right, so we're going to kind of pick up where we left off with simplifying, and we're going to move on to multiplying and dividing because it's very similar. It's a very similar process. So this is still lesson 5.2, and we're going to take a look at some examples. But before we do, I don't want to kind of visit the past. And I want to go back to maybe 5th grade or 4th grade when they started multiplying fractions. And just remember this one thing, that multiplying fractions is one of the easiest things ever. Because the multiplication division rule, parents, basically their famous saying is just do it. So if you have a fraction that you're multiplying, you just do it. You just multiply numerator by numerator and denominator by denominator, and you call it a day, and you're done. And I don't know why some people get hung up on that, but it's just that easy. Sometimes, and maybe this is the reason why, sometimes we have to multiply by a whole number, and that freaks us out a little bit because we don't know what to do. Well, that 3 is simply just is a numerator, okay? It's just a numerator. So the understood number or the understood denominator is 1. So you're just going to multiply 7 times 3, and you'll be done, all right? That's it. Now, division, again, falls into that category of parents that say just do it. And so in elementary school, I know that I was taught this way of, I guess the old saying is, yours is not to reason why, just invert and multiply. And some of you have come up with the phrase lately of keep, change, flip. You keep the first fraction, you change it to a multiplication problem, and you flip it. But maybe you don't even know why you do that. And I want to show you why, because you really don't need to do that. First of all, I want to just start with showing you that for every division problem, there's a multiplication equivalent. We get the same exact answer either way. One is a division problem, and one is a multiplication problem. To obtain or to convert between one or the other, you keep, you change to the opposite signs, and you flip or take the reciprocal, and you get the multiplication equivalent. Okay, with that being said, why do we have to do that? Well, we really shouldn't have to if the parents are say just do it. Let me give you an example. If I had 12 fifths divided by 6 fifths, I'm not going to invert and multiply. 12 divided by 6 is 2. 5 divided by 5 is 1. So the answer is 2. Well then, why am I having to keep, change, flip all the time? And that goes back to that old saying, yours is not to reason why, just invert and multiply. So I'm going to change this to the multiplication equivalent. I'm going to keep, change, flip. And as a result of this, and I don't guess I need to explain that you can strike out those 5's, and 12 over 6 is equal to 2. You get the same exact answer. Now, why is it that we always use the keep, change, flip method? Well, that's fairly easy because not every problem is going to be so. I was very strategic about how I chose those numbers. If I went this direction with it, then it's not going to work out so well. So the best alternative here is to flip it and multiply. And you get the same exact answer as if you were to divide that. So this would equal 21 over 16. Now I say all that because it's important that you understand why. Just simply that. And I think it deserves a little bit of attention. So when we look at algebraic fractions, such as 3x over x squared times y times 2y over 5x. There's a couple different ways you can do this. You can strike while the iron's hot and just start striking out equal forms of 1 or fancy forms of 1. Or you can multiply numerator by numerator, which is what I'm going to do here. denominator by denominator. I have 3 copies of x. I have a 5, I'll put it out there in the front, and I have a y. And this is not simply reduced. Now notice you have the absence of plus or minus signs here. So you don't have to worry about that whole striking out when you're not supposed to, implied parentheses that we talked about. We can just go ahead and do so. So I am given permission to strike out fancy forms of 1. And those fancy forms of 1 is anything divided by itself. So that's a fancy form of 1. I can also subtract exponents. So in this case, what I'm going to get is 6 in the numerator. And in the denominator, I'm going to have 5x squared. Because I can strike out 1 copy of x in the numerator with 1 copy of x in the denominator, leave me with x squared. An equivalent answer might be 6/5, if you subtracted the exponents, x to the -2nd. Okay, so those are both the same. So let's take a look at one that's maybe just a little bit more sophisticated, such as x plus 3 over x squared plus 7x plus 12 times x squared minus 4 over x plus 5. All right, so the first thing we need to do is we need to factor everything so that we can strike out fancy forms of 1 like we talked about earlier. We cannot strike out this x with this x, this 3 with this 12 because of the implied parenthesis rule. So I'm going to go ahead and I'm going to quickly, and if you don't know how to factor at this point, come see me. This is equal to x plus 3, x plus 4. And x squared minus 4 is the difference between 2 perfect squares. So it's x plus 2, x minus 2. Now at this point in the game, what I'm going to do is I'm going to list the restrictions. And the restrictions are x cannot equal -3, -4, and -5. And now I'm going to go ahead and strike out my fancy forms of 1, which I only have 1 set. That's the only thing I can strike out. So I can leave my answer as factors, or I can multiply them back together again. I'm just going to leave them as factors. And then you want to include the exclusions. So that is how you would multiply a rational expression. Again, let me just walk you through the rules. You want to factor everything. Factor numerators, denominators, anything you can. You want to list the restrictions next. And then you can strike out those equivalent factors. All right, let's take a look at division. All right, I'm going to start out with x squared minus 25 over x squared times, or excuse me, this is division, divided by x plus 5 over, or excuse me, I wrote that wrong, let me back that up. X plus 5 divide over, let's just say 3x. All right, so what we're going to do first of all is we're going to factor everything. I'm going to start with this piece right here, and that's the difference between 2 perfect squares. So that's x plus 5, x minus 5. And x squared can't be factored, and neither can the other 2 pieces be factored. Now I'm going to list the restrictions because that's important. I have 2 copies of x here, neither one of those copies can be 0. I have a 3 times an x here. That copy can't be 0 either. So you only have to state that x cannot equal 0 one time. But here's the kicker. When you flip, when you change this over to a multiplication problem, what happens is the x plus 5 winds up in the denominator and the 3x in the numerator. So now we have an additional restriction. So x can now not also equal -5. All right. That only happens here. You don't do these here because that one doesn't change. It's, remember, keep, change, flip. This is the only one that flips over. So that's the only problem we have to look at. And now we can go ahead and strike out equal factors. So I can go ahead and strike out this x plus 5 with this x plus 5. I can strike out one copy of x here with one copy of x here. And now we got to put Humpty Dumpty back together again here. So we have left over in the numerator a 3 and an x minus 5. And in the denominator we have an x. And then our restrictions are right here. And that's just as much a part of our answer as the answer itself. Okay? So again, don't be killing kittens here on me. Don't be striking out these x's. You can't do it. They have to be equal groupings or equal factors. And that's how you multiply and divide rational expressions.